In this video, we're going to review how we determine whether or not when a compound is dissolved in water, it creates an acidic solution or a basic solution. By acidic solution, we mean the hydronium ion concentration is greater than the hydroxide concentration. Of course, a basic solution is when the hydroxide concentration is greater than the hydronium ion concentration. So in front of us, we see the formulas for three compounds, and as it turns out, these are three ionic compounds. And let us assume that they're all, let's say, 0.1 molar solutions. Now, in dealing with ionic compounds, we need to separate the ions. That is, we need to identify the cation and we need to identify the anion. And if you can think of it in terms of this idea, potential. And the idea is that the cation is always the potential acid and the anion is always the potential base. Potential acid, the potential base. The potential acid and the potential base. Okay, so let's take a look at the magnesium chloride. So we've got magnesium ions and we have chloride ions. Now, it is very important for you to remember your chart that concerns who are the super 6 strong acids and who are your strong bases. That is the alkali metal hydroxides and the alkaline earth metal hydroxides. Magnesium is found in the second column of the periodic table. It is an alkaline earth metal. Therefore, its hydroxide in the form of magnesium hydroxide would be a strong base, and this magnesium ion is therefore a negligible acid. In a similar way, the chloride anion comes from a strong acid, hydrochloric acid. As a result, this is a negligible base. Therefore, a 0.1 molar solution of magnesium chloride, I would expect at, let us say, 25 degrees Celsius, to have a pH equal to about 7.0. In other words, the hydronium ion concentration would equal the hydroxide ion concentration. Now, often in these questions, we ask you to write out hydrolysis equations. That is, how will these ions interact or react with water? Well, neither the magnesium ion nor the chloride ion react with water. So we don't increase the hydronium ion concentration, we don't increase the hydroxide ion concentration. So moving over to our potassium hypochlorite, the potential acid ion is the potassium plus 1. The potential base anion is the hypochlorite. So in these questions, it's actually very important that you know about your polyatomic ions. So if you've got your chart of polyatomic ions handy, this would be helpful for doing this sort of analysis. Again, the potassium ion is an example of a negligible acid, as potassium is found in the first column of the periodic table. It is an alkali metal. Its hydroxide would be a strong base. Therefore, the potassium ion itself is a negligible acid. Hypochlorite, on the other hand, is an example of a weak base. Hypochlorous acid is not a strong acid. A hypochlorous acid, therefore, is a weak acid, and that gives rise to the conjugate base, which would be a weak base. Now, in this case, we can actually write out an hydrolysis reaction, which would indicate that the pH should be greater than 7 at 25 degrees Celsius. And as such, also, if we compare the hydronium ion concentration to the hydroxide concentration would be greater. The hydrolysis reaction would look something like the following. So we would have the hypochlorite. It reacts with water. It's going to pick up a proton from water to form hypochlorous acid, and thereby increasing the hydroxide ion concentration over the hydronium ion concentration. This is the hydrolysis reaction that would need to be written out in this particular case. So for the next example, we have the ammonium nitrate. So the ammonium ion. Now note, any cation has the potential to be an acid. If the cation is not an alkaline earth metal ion or an alkali metal ion, any other cation besides those would be considered to be a potential acid. The ammonium ion is a classic example of something that is a weak acid. On the other side, we have nitrate. So nitrate comes from, in a sense, nitric acid. That is, nitrate is the conjugate base of nitric acid. Nitric acid is a strong acid. Therefore, this would be an example of a negligible base. So the hydrolysis equation in this particular case would involve the ammonium ion. Now, actually, let me just come back here just to make the point. We would expect, therefore, that the pH should be less than 7. We would expect the hydronium ion concentration to be greater than the hydroxide ion concentration. And yes, the hydrolysis reaction would look something like this. We would have ammonium ion reacting with water. It reacts as a weak base, therefore it will donate its proton, thereby increasing the hydronium ion concentration over the hydroxide ion concentration. And yes, we would form the weak conjugate base. Now, just to add to this review, you may remember that we can actually calculate what would be the pH of each of these different solutions. All we need to have is the Kb and the Ka respectively. Now, I'm not going to do the calculation, but just to highlight the idea that if we had the Kb for hypochlorite, well, then we could determine the hydroxide ion concentration. And the shortcut equation for this is hydroxide ion concentration is equal to the hypochlorite concentration, in this case it would be 0.1 molar, times the Kb for hypochlorite, all to the square root. Now you may remember that came from using an ice table and solving for X. And X in this case is the hydroxide ion concentration. Now to use this equation, remember that you have to state the assumption. So state assumption, and the assumption in this case is essentially that the hydroxide concentration, or X if you will, is very much smaller than the original hypochlorite concentration. And also remember that you need to do the check. Now the check calculates what the hydroxide ion concentration is that you calculate, divided by the original hypochlorite concentration times 100%. And remember, the check is valid if smaller than 5%. All right, so it's a classic calculation to find, in this case, the hydroxide concentration. Once you have the hydroxide concentration, you can find the pOH and therefore the pH. Conversely, if we are given the Ka for the ammonium ion, or if we're given the Kb for the ammonia, we can also do a similar calculation. So to calculate the hydronium ion concentration, it would equal the original ammonium ion concentration, in this case the 0.1 molar, times the Ka, all to the square root. And yes, you've got a state assumption, and you also need to do the check when you do this sort of calculation. So I hope that you have found this very brief overview of acid-base chemistry helpful in your review for the final exam.